Hello, and welcome back to Sensors and Sensor Systems. This mini lecture covers resistive touch sensors and their companions, resistive touchscreens. As their name suggests, resistive touch sensors work by generating a change in resistance when a touch is initiated. That touch can be initiated by a person's finger, a stylus, or other appropriate device. Even a meteor or an alien can provide sufficient force to trigger a resistive touch sensor. Unlike capacitive touch sensors, the only thing that matters is something is exerting enough force to cross the air gap between the two electrodes shown in green here, and thereby creating the appearance of a touch. Most resistive touch sensors are just switches. They're either on or off, they detect touch or no touch, but no variations or gradations in between. The detection of that touch is independent of the electrical or dielectric properties of the object that is creating the touch. It's just all about force. And for this reason, the resistive sensor is pretty impervious to dirt, soil, moisture, and other contaminants that may occur or materialize on the surface of the sensor. Again, because they're detecting force rather than a shift in electrical properties which could be affected by dirt, soil, moisture, and other contaminants. So it's no surprise then that resistive sensors are used a lot in outdoor applications where dirt, moisture, soil, and other contaminants are in plentiful supply. So one way to approach resistive touch sensing is just basically to measure resistance at every possible point in the array. For example, in the 3x3 array here, shown here, there's a wire to every single pixel in the array. And depending on what's going on with the touch, you have one of two things going on. Either that load resistance to VDD is open, indicating no touch. Here's our load. This is the no touch condition when there's no contact between the top and bottom electrodes of the touch sensor. Or, alternatively, there's a short caused by a touch, a force that's sufficient to make contacts between the two electrodes. So this is the touch condition, and it results in a output voltage here of 0 volts, indicating touch. And the no touch condition results in an output voltage of VDD. There's no current through RL, so the voltage drop across it is 0, and therefore the output voltage here is identical to the voltage here, which is VDD. And while this approach can detect multiple touches, it consumes a lot of space and power. Running all those wires and resistors takes a lot of real estate, and it quickly becomes prohibitive for all but the lowest of resolution screens. So instead, what we can do to more efficiently approach measuring touch in a touch sensor screen using resistive technology is we can use two plates. Instead of a pair of electrodes at every pixel, for the entire array we just have two different plates. And we either apply a voltage across one plate and measure the resulting voltage on the other plate, or vice versa. So here we could apply a voltage across the blue electrodes and measure the voltage at one of the red electrodes, or we could apply a voltage at the red electrodes across the red electrodes and measure a voltage at one of the blue electrodes. Both of those will give us an indication of a single touch on the screen. So what we have here when we use the two conductive plate method is simply a voltage divider. Wherever the point is located on the resistive touch screen, the voltage divider in the row direction or in the column direction will indicate where that single touch is located. So let's take a look at how this works in terms of circuit analysis. So here in this example, we have a touch screen, a resistive touch screen consisting of those two electrical plates, two conductive plates, one right on top of the other. And where we put the touch, we are putting a touch that's 3/4 of a way across the screen from left to right and 1/2 of the way down, about right here. So this is 3/4 of the screen here, 1/4 here, and then in the other direction we have 1/2 of the distance and 1/2 of the distance on either side of the touch. So with voltage divider, when we now apply a voltage at Y plus, which is located right here, Y plus and Y minus on top and bottom of the screen. So we're now applying VDD from Y plus to Y minus, Y plus, Y minus, and connecting Y minus to ground. And now there's a touch here that's splitting up the total resistance from top to bottom in the screen. So we can model that as two resistances, 1/2 of the total resistance on top and 1/2 of the total resistance on the bottom. And now if we measure this point at either X plus or X minus by voltage divider, it's just going to be 1/2 of VDD. When we do it the other way and now apply a voltage across X plus to X minus here, we put VDD at X plus and X minus we connect to ground. Then we also have a voltage divider, except in that scenario we have 3/4 of the total resistance of that total resistance before the touch and 1/4 of the resistance after the touch. And by voltage divider then, if we measure the point where the touch is across the Y direction, either at Y plus or Y minus, we get 1/4 of R over R total times VDD is the voltage here. So we essentially get VDD over 4 by voltage divider for this touch right here, 3/4 of the way across the screen. So clearly this is a pretty simple and efficient way to measure a single touch, but it's terrible at measuring multiple touches. So for that reason, resistive touch sensors and touch screens for the most part are used to measure only single touches. So in short, resistive touch screens, they respond to finger, stylus, glove, etc. Anything we want that's capable of applying a force to the screen can be used to detect touch. They are highly resistant to dust, dirt, and other elements. They can be very high resolution when we use the two-conductive plate method, and they are pretty well suited to capturing handwriting. But they're also not very sensitive, and they require a lot of pressure relative to capacitive touch screens to respond. They often have poor contrast and display quality, and they definitely don't support multi-touch. They're also vulnerable to failure based on damage to only a small part of the screen, where dead zones can develop based on too much use. But resistive touch sensors and touch screens have their place in the world. They are generally used in outdoor applications or applications where a very robust screen that can tolerate a lot of abuse is needed. When a more subtle screen is needed, or we need a screen that can handle multiple touches, we have to move to capacitive touch sensors and touch screens. But resistive touch sensors are very good for applications where there's a lot of abuse and mistreatment of the screens themselves. So that's just a short overview of resistive touch sensors and their related touch screens. Thanks for joining us, and we hope you'll join us again soon.